Retro.
Yeah.
Electro. Tech.
Oh yeah.
Hey, turn the lights back on. Wow. Retro Electro Tech. When real audio ruled the world.
Well, hello there once again, ladies and gentlemen. This is Retro Ernest of Retro Electro Tech. And I'm back on this Sansui 3900Z, that's 3900Z, digitally synthesized DC stereo receiver. Pretty fancy. Somebody pinch me, just not too hard. I'm kind of sensitive.
Ouch.
I'm back in cleaning up the mess that I pointed out in the preliminary evaluation video, which was a few months back, and I had to shelve it, circle around, and I'm back to it. As you can see, I've got some parts on order. I got parts pulled out. So anyways, that's where I am. So I'm going to address the parts that I have pulled out, why that is, and kind of show a few things as far as some brief testing on a few parts and go into that. I will mention that aside from the parts I pulled out, I was in here doing some in-circuit testing, just spot checking, looking for out of tolerance resistors, things like that. I found some open resistors. I found some things that, of course, had to be pulled, addressed as I was doing my forensic analysis as to why we had a shorted output transistor, which I mentioned in the previous video once again. So I showed that we had full rail voltage on one of the channels. So I'll get into that a little bit more, kind of break things down. I'm going to get some things cleaned up. All this heatsink compound that was slapped in there, there's way too much applied. Actually, what you see in here is only a little bit. I cleaned some of it out. Some of it was all degraded and just kind of fell away, like it was kind of powdery and chalky and just kind of fell away. But yeah, there was a lot of it and whatever. But I'm going to go into the breakdown anyways, and let's go ahead and get into that. Okay, so I got some components here laid out on this pretty gray piece of paper in an organized manner. So let me just start by saying there's the shorted output problem that I touched on earlier that I'm going to go into first, involving the right channel. And let me just say, even though I have these output transistors here on the left, well, these are actually the right channel. Go figure. So, just the way I threw them down on the paper, so good enough. But anyways, let me just show you here. This is the shorted output transistor here. So again, this is the right channel, PNP, and let me go ahead and just demonstrate the junction testing. So our pinout is base collector emitter, and by the way, this is a 2SA1102. These are the original transistors on the right channel, 2SC2577, and again the 2SA1102. PNP, base collector emitter. So we're going to want to put our black probe on the base and read across the collector here. And you can see that forward drop there it's too small. It's not typical. So same thing on the emitter. All right. And if I check between collector and emitter, we're shorted, collector to emitter short. Swap the probes around, same thing. We shouldn't be reading anything there. So if you notice the neighboring PNP over here on the left channel, well, and again, even though it's on the right, you'll notice what it should be doing, and these are not the original outputs. These are substitutes, and somebody used a 2SA1106, N is in November, and a 2SC2581. Neither here nor there really, but let's just go ahead and take a look at what a typical PNP looks like during just a quick down and dirty junction test. So negative probe on the base once again. That's more of a typical drop, somewhat, emitter. Now when we go between collector and emitter, we have nothing, okay? swap them around, same thing. We should have nothing. And that's the case. Nonetheless, though, these outputs are going to all be changed out. I want to start with some transistors that are better matched between each other, and just fresh output transistors. So I'm not going to get into all the HFE gain matching and all that. That's not always super duper crucial at the outputs, but anyways, I want to start with fresh outputs and go from there. Also too, based on my findings involving this right channel here, there was a driver transistor, this one here, I believe, what is it, a 2SB 631K. So yeah, now this this driver transistor was sporting a 100 ohm open emitter resistor. So an open 100 ohm emitter resistor, okay? This emitter resistor here, it's blown open. So there's that. And on this topic of open resistors, on the right channel power rail, there was this open 4.7 ohm quarter watt fusible resistor. Now, it did what it was supposed to do when this channel ran away, so that's good. So there's that. And what else? There's a few things I want to touch on. Oh, on the topic of open emitter resistors and all that. By the way, these emitter resistors associated with the outputs are fine. I wanted to check them out of circuit, pull them out, check them, and they're looking good. Not a problem. So there's that. And what I wanted to mention too is that I found a lot of bad solder joints and damaged solder pads, all over the areas where previous work was performed. So I have a lot to do there with reflowing and some repairs. And I think in the previous evaluation video, the preliminary evaluation video, I scrolled along the back side of the board where these, mainly where these outputs were mounted, and I was showing you guys some shabby solder joints, and I think I pointed out that there's some damage on the pads that I could see, all that kind of stuff. But there's more. When you really look around, there's a lot of crappy solder joints and damaged pads. And on that note too, because I'm just kind of going through and pointing out in brief, I'm not going to get into a lot of detail. Some of these components I am going to do a little more testing, like these drivers. I'm going to show that these drivers are actually pretty good. In fact, the transistor with the open emitter resistor, the 100 ohm emitter resistor, the transistor itself is looking pretty good, and I'll demonstrate that. So next, and I think it had more to do with bad solder joints, is these bias trim pots here. They're old and shabby anyways, so I don't want them in there, but when I was first checking them and just kind of ohming them out, they seem to be a bit on the intermittent side. But again, when I flipped things around, I saw that there was some real clunky, crappy looking solder joints associated with these. So anyways, I pulled them out, and when I pulled them out and I was I kind of cleaned them up real quick. I sprayed some contact cleaner on them. I was running them through their ranges and all that while I had them hooked up to an analog meter, and they were doing okay at that point. So I think that it was just in circuit with the funky solder joints and whatnot. But like I said, I'm still going to get rid of them. In fact, I have a couple of, they're in place, but they're not soldered in. And I'll pan over in a little bit when I start getting into this more and show you guys. But I have some multi-turn Bourne's pots already in place. I had them in stock, 1K trim pots. So there's that as well. And also too, another thing that I want to touch on that's really important is the whole situation with thermal regulation. I touched on the fact that there was just way too much heatsink compound applied. More isn't better in this situation. In fact, less is more. In order to establish good heat dissipation and nice efficient thermal regulation and heat transfer, all that stuff, between the output transistors and heatsink and whatnot, you need to apply a fairly thin and even, that's the key, even, fairly thin and even layer of good heatsink compound. And between the of course the back of the transistor and the surface of the mica pad, and between the surface of the other side of the mica pad and the surface of the heatsink. So that's what you want. You don't want big globs of heatsink compound and thinking that, well, you know, it's heatsink compound, the more you put on the better. No, that's not the case. So there's that. And on that note too, what we have over here, and another problem, is bad mounting and lack thereof actually, involving these TO92 package bias spreader transistors that mount to the heat sinks. So, you know, because they mount to the heat sinks and what they're involved in, they're crucial links in the thermal monitoring and regulation chain, in other words. And of course, in order for that to happen and for these to thermally track or follow the outputs, all of these transistors, you know, the outputs and these bias spreaders, they need to be properly mounted to the heat sinks as well, and these were not. And what I mean is, on the left channel here, this left channel bias spreader transistor was in contact with the heat sink, but it again had way too much heat sink compound, and because of the manner in which it was mounted or pressed against the heat sink, I don't feel that it was very adequate. I think the method that they used, which basically was just a piece of spring metal, and I'm going to point that out, pushing against the transistor, pushing it against the heatsink, was pretty cheesy. And this right side bias spreader transistor was not even in contact with the heatsink at all. Surprise, surprise. In fact, it was about maybe a quarter inch to half an inch away from it, and missing that little piece of spring metal that normally would have pushed it against the heat sink. And again, I'm going to show that in just a bit. So this right channel had a lot going against it, and I think obviously we were dealing with a thermal runaway situation, and there's that. And I'll get more into that a little bit in just a moment as I get into things. Okay, now I'm going to get into some down and dirty component testing. I'm going to get through this quick. Obviously, of some of the components that I pulled out of the unit that I had laid out that I was talking about. So I'm going to start with one of the driver transistors, the one that has the open 100 ohm emitter resistor associated with it, which in turn is the driver transistor that drives the, or was driving the failed output transistor. So anyways, let me go ahead and check that out. I'm going to test all the drivers that I had laid out, but I just want to start with that one because of its association with the failed output. Now, when I was going through, I spot checked it just in diode check mode, just to test the junctions to see if, you know, it was shorted or had any open junctions, anything like that, any problems. But it looked perfectly fine. But I still want to, you know, check the gain range and check for leakage and what have you. So let me go ahead and start with that. So away we go. All right, we're all zoomed in and ready to go, better than being all dressed up with nowhere to go. So a little bit of an afterthought, I decided I would touch on a few things going on here for some of the newer ones. And first of all, we're hooked up to a 2SB631, and that's a PNP transistor. It also has a letter E that serves as a classifier or designator. I'll talk about that in a little bit. And by the way, I'm not going to cover the big transistor topic, just, you know, more specific to what I'm doing here, this transistor, but some of the information is going to be applicable across the board. So there you go. So first off, as far as the pinout is concerned, just be aware of that, because pinouts will differ, and you need to be aware of that and how that compares with what you're replacing, and, you know, how the board's laid out there as far as the through holes and all that. So you don't want to drop the transistor in incorrectly and have problems. So in this case, from right to left, we have base collector emitter, and you'll notice that there's, you know, some color coding on these probes. Green is typically hooked up to the base, red is hooked up to the collector, and blue to the emitter. So there's that. So just be aware of that. And also too, when you're handling a transistor, especially when you're gonna gain test it, don't handle it by the body with your fingers. These are temperature sensitive. That will influence your measurement. It will influence the gain, and there you go. So just be aware of that. Now, if you're just junction testing with your DMM and you're just in diode mode and you're doing a pass-fail test and just testing the junctions for shorts or whatever, not a big deal, because that's not about getting a more accurate reading on a meter. It's just pass-fail. So there's that. Now back to the E on this transistor, this series here. So there's a general gain range. If you look at a data sheet, or if I was to look it up in this transistor manual, it's going to give me a general gain range that these various transistors in the series that have these classifiers shown as letters are all going to kind of fall into, okay? And I think there's three different classifiers, okay? There's the letter E on this one, and if we were to look at its complement or its girlfriend, the 2SD 600, there's a letter F. Okay, now with this one here, again, I said that the general, or maybe I didn't make note of the general gain range. If you look at a data sheet, it'll show you that. It'll show you a minimum and a max. In this case, it's I think 60 to 320. Whereas if we hone in a little further on the letter E, the classifier there, or designator, and you scroll down a little bit more, there's usually a box on the data sheet, and it will show the the classifier there. And in this case, E is between 100 and 200, so that narrows it down a little bit more. So there's that. So anyways, let me set this aside and get to testing this transistor. So I had to move myself around over here because I want to be able to see the display a little bit better. So first off, we know we have a PNP hooked up, and on this tester we have a knob here that toggles between off, NPN, and PNP. So switch it over to PNP, okay? And we see that needle is falling shy of the number 2 with the little line there at the end of the scale. Well, we want to calibrate it till we get it right over that line. Now, being that I'm not looking at this head on, I don't know if I'm right on it, but I'm close enough. Yeah, right about there, I think. It's good enough. So, because we also know based on our data on this transistor that we're going to be, or should be, ideally, if the transistor's looking pretty good, we should be between 100 and 200 on the HFE, the gain. So that being said, this switch here, times 1, times 10, I have it on times 10, and now I'm going to just hit this test switch and see where it takes us. Yeah, it looks like we're right about 150. So yeah, that's looking good as far as our gain is concerned. And this tester like this will get us in the general ballpark. Yeah, it doesn't exactly mimic the native circuit that this is operating in, but if you know what the limitations are, you know what you're testing, then you can extrapolate from there, and you can figure that, yeah, that's just about right. So good enough. Now for a leakage test, if we swing our knob to the left, that will give us a collector to emitter leakage reading, and then over here to the right, collector to base. So let's do collector to emitter, and you see the needle dropping all the way down to the bottom. Well, these silicon BJTs and all that, low signal transistors, typically have very, very low leakage, should have very low leakage if they're healthy. And we're down there way at the bottom of the scale, so we're looking good. Very low leakage, okay? Collector to base, again, very low, and that's what we want. So when I test the other transistors, the other drivers, if they're, again, if they're all in that ballpark, as far as the gain is concerned, and there's going to be some variance, but as long as they're in that general ballpark, based on the data that we have on these and whatnot, we're looking good. And same thing with the leakage. As long as there's low leakage and all that, then great. If not, then I'll chime back in and point it out and show you on the tester what's going on if there's any problem. But other than that, if not, then this is the final mention of that. Let's go ahead and move on. Okay, now I'm going to test a few electrolytics pulled from the power supply. Matter of fact, let me reach over and grab these. And by the way, the other driver transistors tested just fine, so great. But anyways, in the preliminary evaluation video, I pointed out these caps in parallel that were installed in place of the originals, okay? Now, on that note, the originals, which were just single can capacitors sitting on the footprint, which is why I didn't like these there. This is not the level of work I like to do. I'm sure that the people that installed them, maybe this is what they had on hand, but there's also some other reasons why, you know, I wanted to pull these caps to begin with, other than the fact that, you know, I didn't want these caps in parallel sitting on that footprint, and, you know, especially now that my name's associated with this unit. So yeah, the originals are 6800 mics at 50 volts. These caps individually here are 3300 mics at 50 volts. So some of you know that when you parallel caps, that your capacitance doubles and your maximum voltage remains the same. So even if these caps are in good health, and, you know, at best we're going to get right around 6600 mics, and remember, the originals are 6800 mics. So, you know, that alone, you know, I don't like that, because I like to have more oomph in the reserve to, you know, really hold up the power supply and deliver in terms of just holding up the power supply and filtering and all that. So typically I will even up the up the capacitance a bit carefully. If I can do that safely, then, you know, and that's another topic I'm not going to get into, but I typically do that because I like, again, a little more oomph in the reserve, and there's that. So what else? Because I was going to say something and I got a little distracted because I heard something outside. But yeah, anyways, in parallel, these are still a bit flaccid, and, you know, I'm going to test them to see what they're doing in parallel anyways, what they're actually reading. And yeah, there's going to be tolerances, plus and minus, but in my experience, when you're dealing with good quality caps from reputable manufacturers that produce, you know, really good series of caps, despite the tolerances, they're going to be pretty darn close in that ballpark to the rated capacitance on the can, okay? So I'm replacing these. I'm going back to 6800 mics at 50 volts. Of course, I used, I can't remember now because the caps are on their way. I ordered them, but I think I ordered some Nichicon. They're long life caps, higher temperature, 105C, with other good characteristics as far as ESR and ripple handling capability, all that stuff. Good power supply caps. Whereas these here, I know they're just kind of an off-brand Taiwanese cap. That doesn't mean that, you know, they're horrible Taiwanese or even Chinese caps sometimes. It depends on quality control and the process, the manufacturing processes, quality control, all that stuff, you know, the chemistry and what have you. So anyways, not going to get into that either, but these caps are not up to my standards, because I like to replace what I'm replacing with top-notch parts from, you know, reputable manufacturers, and also too distributors that buy factory direct, so I don't have to worry much about counterfeits and all that. But that's another story. But anyways, so let me get these on the LCR meter here and see what they're actually testing at, and go from there. So let me do what I got to do. Set our test frequency at 120 hertz. These are power supply caps. So, and let me go ahead and clip on and see what we got going on. So, pardon me just a moment here. So, looks like let me get our ESR into play here. So it looks like capacitance wise we're at about 5600 mics, right about there, microfarads, mics, and our ESR is unreadable, or, you know, on this meter, which tells me it's nice and low. It's not even measurable, so that's great. And I'll talk a little bit more about the ESR and caps and capacitor and parallel, real brief, but anyways, so you can see that these caps are really underperforming in the capacitance department when we consider that the originals are 6800 mics, and there you go. So I'm not even going to bother reading the other parallel pair. I'm just going to mention though that the only benefit I see to doing this, of course, it would have been better if they would have used, capacitance values that would have measured up, after putting them in parallel and not, but anyway, that's another story. Won't get into that. But as far as the ESR is concerned, you notice we had very low ESR, and most good electrolytics, especially nowadays, high quality electrolytics, they're gonna have lower ESR. They're going to be good quality caps and all that. So, but the only benefit I see to really paralleling some electrolytics is if you're doing that for the purpose of lowering ESR, okay? Because think about the internal resistance, the ESR that's inherent to electrolytics or any cap, but electrolytics, typically, you have higher ESRs, but think of the inherent or internal resistances as just that, well, resistors. So if you take two resistors, put them in parallel and measure, end to end with two resistors in parallel, well then your resistance measurement is going to be lower than any of the one single resistor values. So in other words, if you had two 10 ohm resistors, let's just say exactly 10 ohms in parallel, well then you're going to get a reading of 5 ohms. So you can see that resistors in parallel result in a lower resistance. Hence, if you take these caps as they did and parallel them, then their internal resistances are going to be lower. So that's the only benefit that I could really see, which I doubt if that's the reason why they did it. They probably just had these on hand, decided to use them. And like I said, they're underachievers in the capacitance department. So anyways, let me go ahead and move on from here. So now I want to quickly measure some resistances, and I mentioned, or at least I believe I mentioned, that the bias VRs, trim pots, these here, were exhibiting some intermittent behavior, and I think that was on account of the solder joints that were holding them to the board. The solder joints were pretty shabby. When I was checking them out in circuit and just clipping on and reading end to end and reading from one end to the wiper, other end to the wiper, just going through with a screwdriver and rotating them around, monitoring the needle on the analog meter here, I was seeing some dropout. Things were getting a bit fickle, so after I desoldered them, pulled them from circuit to check them once again, just real quick, things were okay for the most part. I mean, I didn't spend a lot of time messing with them and manipulating the VR back and forth, and really working them and all that. But these are old crusty VRs, so I pulled them out because I changed them out anyways. I have some multi-turn Bourne's pots sitting in their place. After I end this section, I'll zoom in when I get ready to close things out, and kind of check some things out and have some final words. But anyways, let me go ahead and just check these real quick on camera. So I'm setting the meter at times 10. I'm going to short the probes and null out the needle there. Actually, it's pretty spot on. Okay, so it's nulled out over here at 0, right over the line, so we're looking good. So let me clip on for starters, and I'm not going to read both of these crusty old VRs, but I'm just going to go end to end. That's each end of the resistive track before I clip on to the wiper and run it through its range of travel. So I'm on times 10. You can see the needle lifted to just below 100, so we're pretty close to 1K, and that's pretty good. So let me clip on to one end and the wiper, and let me get the screwdriver in here and kind of steady it out and try not to lose contact. But you can see if I rotate this VR through its range, it's looking pretty good and consistent. So I have a feeling it was the solder joints. But on that note, like I said, old crusty VRs, it's good just to install in this case because, you know, I was able to do it, had the budget to do that. So in this case, it was good to get them out because if something goes wrong and the VRs get fickle and, you know, open up or drop out or whatever, then you know, you'll lose control of the bias and bad things will happen. So since I'm on the subject of reading resistances, here's the 100 ohm, and let me just drop down to ×1. I'm not even going to bother you know, nulling it out. You'll get the point. So this is the 100 ohm resistor associated with the emitter resistor that's associated with that driver transistor that I measured earlier. And you can see I'm clipped on and we have nothing. It's just open, like I said. And then the 4.7 ohm fusible resistor on the right channel power rail that opened as well. You can see I'm clipped on. Zero, zilch, nada. So anyways, that's what I wanted to point out. I went through just some down and dirty testing, and the point was to support what I was talking about when I was going through the parts I had laid out and was explaining, you know, the chain of events that led to the right channel failure and all that. I wanted to, you know, sort of back it up a little bit with, you know, some measurements here, because I'm going to pass this video to the owner of the unit as well. And as I probably mentioned before, and I think I mentioned already, I don't know if he's a type that likes this stuff, but I'm sending it to him for the record anyways. I don't mind doing it this time around. Can't do it all the time, but, you know, whatever. So anyways, let me go ahead and swap views again and move on. Okay, here we are again looking into the belly of the beast one last time for this video. And yeah, I still have a lot to do, as I explained throughout this video, but I'll just recap real quick. I want to keep this very brief. So yeah, on that note, recap, I will be recapping the power supply as I mentioned, and here were those footprints where the main filters went, and you know, those parallel pairs were sticking up from each one. But anyways, so I'm going to wrap all that up. I'm going to replace a few caps, you know, odds and ends here and there, namely this cap here that, well, let me actually pan down to it. This cap here that has a little bulge to it, things like that. Clean up what I can as far as, get the crap out of here and straighten up those bad solder joints on the back. I'm going to remove a couple boards here to access the controls and go into a multi-flush cleaning. But I'm not going to really roll footage on the whole servicing of controls because I do that all the time on all of this equipment. So I'm going to spare you guys that this time around. And when I do roll another video, because there will be one, it's going to be just, going in, recapping stuff and getting the other parts on board. So real quick though, let me zoom in on those new bias trim pots. All right, and there they are, multi-turn Bourne's pots, good trimmer pots. So I had to extend the rear legs over here to reach the through hole, as far as these trim pots were concerned. And I applied some insulation to them. They're not soldered in yet. I'm going to tack them in just a little bit. But like I said, I'm going to wait till I go through and get all the other parts on boards, caps, and the new output transistors and all that stuff I am going to show in the video. Like I said, the next video. So in conclusion, and my conclusion, just based on findings once again, yeah, I think, bad things happened on the right channel. That's obvious. A stable operating point, just just probably couldn't be maintained via the bias circuit. That was probably in response to, you know, the increase in current draw, you know, resulting from things heating up and the not so efficient heat dissipation going on. Remember, the way the output transistors were mounted with all that heat sink grease, you know, globbed on, and that lack of thermal tracking and compensation on account of the bias spreader transistors not properly mounted, the one on the right channel not even mounted at all. And, you know, that's what they're there for. You know, temperature sensors, they, you know, monitor the heat, you know, track with the output transistors, and of course control, if you will, the bias circuit in response to that, or cause the, you know, bias circuit to compensate for that. So that should have normally been in place to you know, throttle down those output transistors, you know, before they reach that point of no return. So anyways, that's about it, guys. I'm going to end it here. So as I always say, guys, peace, love, music, and the vintage audio that brings it to your ears. Till next time, y'all take care.
This has been a Spinning Head production.